Okay, welcome to a triangle process on regular graphs. This talk is given by me, Colin Cooper, and it is joint work with Catherine Greenhill and Martin Dyer, and you can find the relevant papers on archive at the titles are as shown. So the talk is in three parts. The first part is an introduction to sort of classic work on switch processes. The second part is just an introduction to triangle switches, defining what they are. And the third part is a brief sketch of the fact that triangle switches are irreducible on D regular graphs for D greater than or equal to 3. So the first part, switch edge transformation of a graph. We take a random pair of edges, so the edges chosen there are X, Y, W, Z, and we switch them to another pair of edges. So there's three choices. We can choose the original pair of edges, the edges X, W, Y, Z, or another pair. And in the example shown, we've switched them for X, Y, W, Z to X, W, Y, Z. If the thing we get at the end is not a graph, if it has loops or multiple edges, then we reject the move. And the thing to note is firstly that switches are reversible, because if we can switch from left to right, we can switch from right to left at the next move. And with probability at least a third, the graph is unchanged, because if we pick the original pair of edges, we've got the original graph back. So this means that the chain, as a Markov chain, will be aperiodic, as we mentioned in a moment. Okay, so switches are an example of graph transformation. It's a way of moving between graphs by just changing a pair of edges at a time. And the thing about switches is they don't change the vertex degree, because if you look at this thing, the vertex X loses an edge and the vertex X gains an edge, so nothing changes at the vertices. So it's the transformations within the space of graphs of a given degree sequence. And there's an example at the bottom of the page of a graph with degree sequence 1, 1, 1, 2, 2. Okay, so a few facts about switch Markov chains on fixed degree sequence graphs. They're irreducible. It was proved by Taylor in 1981 that you can get from any graph to any other graph in space. They're aperiodic because, as we mentioned, with probably at least a third, you don't change at any step. And so a Markov chain which is irreducible and aperiodic has a stationary distribution, and switches satisfy detailed balance, so the distribution is uniform. So if we run the chain for long enough, people think then we can sample nearly uniformly from the space of fixed degree sequence graphs. And Cannon and Van Parler were sort of introduced the idea that it could be rapidly mixing in the paper Simple Markov Chains for Generating Bipart Byte Graphs and Tournaments. That was in 1999. The problem is that often the mixing times we get, as you'll see in a moment, are quite large polynomials. They're not all that small, but the experiments suggest that they can be, in reality, they're much faster mixing than this. So here's a general result about the mixing time of switch chains on fixed degree sequence graphs. It's by Greenhill and Fragara, and it's couched in terms of total degree rather than the number of vertices. So that capital M is the total degree. And we're assuming that no vertex has got degree larger than the square root of M. Then the mixing time, which is the number of steps to be within epsilon of the stationary distribution in total variation distance, is given by that formula there. And you can see that that's quite a high degree polynomial, because M, for any sort of connected graph or reasonable graph, M is at least n. So it's at least n to the 10th log n. Okay, now once you've got a chain, the first thing you want to do is you want to sort of play about with it. So typically, the way that we can modify switch chains is to impose further conditions on accepting the switch, restrict the number of edges accepted, restrict the type of switch used. Triangle switches will be an example of that. Or we can introduce other moves in the chain as well as switching, such as adding or deleting vertices. Examples on the next few slides. Okay, so the classic example is where we restrict the edges which are accepted to generate or near uniform generation of perfect matchings. So you start off with some perfect matching of the graph and you pick a pair of edges in it and you switch it with another pair of edges. And if those edges are edges of the graph, then we accept the switch because we've replaced two edges in the matching by two other edges. Otherwise, we reject it. So the example at the bottom shows the edges 2, 3, 1, 8 being switched to 1, 2, 3, 8. Two examples of the other types of switch modifications from computer science. Additional moves. So as well as actually switching, we can introduce and delete vertices. So if you have, for example, a 4 regular graph, and I take two edges and I sort of pin the center of those edges together as shown to make that new vertex U, then I've introduced a vertex. And similarly, if I delete that vertex, I can move back to the pair of edges on the left as shown. So that's an additional move. And the first kind of restricted switch transformation, or an early example, was a flip chain, where we take a path of length 3 and we just switch the two end edges of the path as shown. So A, B, C, D go to A, D, C, B. And flip chains can be used to randomize networks without risk of disconnection, because if the graph on the left is connected, so is the graph on the right. So a flip chain runs in the restricted subspace of fixed degree sequence graphs, which are the connected ones, or the ones connected to the starting graph. Okay, small world networks and triangles. So some time ago, there was quite a lot of interest in small world networks. And there's a sort of folklore which says these things are sparse, they don't have many edges, they're connected, and they have a large clustering coefficient, which means they've got lots of triangles. So sparse random graphs are not good models of small world networks because they don't have many triangles. And there were various attempts to construct sparse random graphs with many triangles, but some of the constructions are a bit artificial, perhaps. In social networks, or social network study, the idea of triangles in a graph has a special meaning. It's called triadic closure, the strength of weak ties. If I know two people, maybe they know each other. So basically, if there are edges A, B, and AC, there may well be an edge BC. Facebook recommends friends of friends, so you may, in that way, lead to triadic closure. And it's interesting to note that triangles can be made. So if two people are friends with a given person, then maybe they will become friends. But triangles can also be broken, because if two people are friends with a given person, they may fall out over that person. They may come to some disagreement over opinions or jealousy and such and such. So here's a restricted switch, which is a triangle switch. And this switch can be used to make or break triangles based on two paths of length 2 from a central vertex. The central vertex on the left is V, and the paths of length 2 are shown on this is rather in the spirit of the flip switch shown earlier, but it's a twist on it. So on moving from left to right, I switch the edges X, Y, W, Z with X, W, Y, Z and make a triangle. And moving from right to left, vertex V is in a triangle and I want to break it. X and W are going to fall out over V. So I pick another random edge, and as long as it doesn't sort of make the graph non-graphic, I make that switch to X, Y, W, Z, which now breaks that triangle. So a typical chain based on this, I mean, there are many possible chains you can dream up, but a typical chain picks a vertex V, chooses the move type depending on the presence or absence of the triangles at V. So, okay, triangle process on D regular graphs. We're going to investigate the triangle switch process on the space of D regular graphs on n vertices. So typical questions include irreducibility. Can you get from any graph in the space to any other? So that's the topic of this talk, but yes, you can. So the space of d-regular graphs is connected under triangle switches. How long does it take to get from any to reach near uniformity or near stationarity? That's ongoing work. And the number of triangles. If you run one of these chains, how many triangles are there in a typical instance of the process after a certain time or near uniformity, and how quickly reached? So we showed in the first of those archive papers previously mentioned that linear bounds can be obtained for the number of triangles in linear time. So starting from any old three regular graph, even one without any triangles, if you run the process for linear time, you can get a linear number of triangles. Okay, here's a picture of a three regular random graph on 100 vertices. It hasn't got many triangles. I think you can see one somewhere on the right. Then we ran the switch chain on this for some number of moves, 510,000 moves, and the graph looks like this. So applying it to this graph, you've got a random graph which is very much not a sort of a uniform, a normal random three regular graph. You can see that there's many triangles, and there's a little K4 is detached at the top right-hand corner. So the main theorem is this. Sort of the state space of the process Bm in D, and edges are joined if and only if we can move from G to G prime by a single triangle switch. So the state space has got vertex set regular graphs of degree D, and we join vertices in the state space if we can move from one to the other by a triangle switch. And basically we say that a time homogeneous Markov chain with this state space is called a triangle switch chain if its transition matrix P satisfies there's a transition from G to G prime with positive probability if and only if GG prime is an edge of the space. So the theorem is that if D is at least 3, then the state space is connected. In other words, any triangle switch chain is irreducible on GND. So any chain which satisfies that condition that there's a positive probability of all triangle switches is irreducible. It doesn't depend on the chain, it just depends on the positive probability of having a switch. Okay, so the basic idea is as follows. I'll just sketch out the basic idea. We're going to assume that n is divisible by d plus 1 in the first instance. And if we're given some input graph G, using triangle switches, we convert it to a graph H consisting entirely of complete graphs on d plus 1 vertices. So if D is 3, then we reduce it to K4s. And then we show that a graph on n vertices consisting entirely of complete graphs can be converted to any other complete graph of the same type by triangle switches. So firstly, we're going to, in this talk, we're going to indicate how to get from one complete graph to another using triangle switches, because if that's the basic idea is to go through the space of complete graphs on d plus 1 vertices. And then we're going to indicate how to detach a complete graph on d plus 1 vertices from the rest of the graph, thus reducing the kind of inductively the number of graph vertices which need to be reduced to kd plus 1s from n to n minus d plus 1, because with positive probability the chain won't touch those complete graphs on d plus 1 vertices. Okay, so here's an example of transforming cliques for d equals 3. And I've got those two cliques there at the top, those two tetrahedrons. And I'm going to use triangle switches to turn it into those two cliques at the bottom right. So basically, I'm going to move the vertex V away from the first clique on the left at the top and introduce the vertex Y. sorry, not the vertex Y, the vertex A instead. So the first move there is I single out this vertex Y and I break that triangle at Y, the triangle YWV, by switching the edges VWAB. So doing that converts the two cliques into a single graph, which is the one shown in figure 2. And now I'm going to sort of reshape that graph. I'm going to switch. I'm going to break the edge YW against the edge AD at X. So once again, I make that switch there. So that's a triangle break move. So now I've made 2 triangle break moves, which is reconfigure that graph to get the vertex A into the first little pair of triangles there, that little diamond in figure 3 at the top left, bottom left. And then I'm now going to make a triangle switch at W. I'm going to introduce the edge AX. And I'm going to do it by switching the edges ACXV, and the resulting figure is shown at the bottom left-hand corner. So that's a sort of a good example of how to fiddle about with triangle switches to move from one graph to another. So now we've shown in outline how to transform one pair of cliques into another pair, and this can be sort of generalized inductively to show that the subspace of all complete graphs on D+1 vertices whose total is n is connected. Okay, so we've got d greater than 3, and now for the moment we're going to assume that n is at least 2d plus 1, because if I wanted to detach a clique, I've got to have enough vertices to break one off, so I need at least 2d plus 1 vertices to remove the clique. So I pick any graph in the space and I take any vertex, which I call a designated vertex, because the proof is going to focus on that vertex. I'll let S be the closed neighborhood of V and G, so that's V and its neighborhood. And then we can prove that there is a sequence of triangle switches which ends at a graph G prime, which has a complete clique component on the vertex S at S. So basically, by a series of triangle moves focused around the vertex V, I can completely detach V and its neighbors from the rest of the graph. And therefore, I've sort of, that vertex is now in a clique, and I've reduced the remaining number of sort of large components which needs to be processed. Okay, so here's a picture. Here's V. Above it is N of V, and above it is N2 of V, its second neighborhood. And well, there's nothing to prove if there's not at least one non-edge between the vertices of N of V, because if there's no non-edges in N of V, then the thing is already a clique on D+1 vertices. So what we're going to do is we're going to use triangle switches at V to increase the number of edges between vertices of N of V. And this can be done in a way which never decreases the number of edges between vertices of N of V. So we may change the edges in N of V, but we never decrease the number of edges induced by the neighbors of V, in the number of edges in the sort of the induced graph of the neighbor set of V. So eventually, if we keep introducing edges into N of V and never remove any, at each step, the number of edges increases by 1 until N of V is completely full of edges, and it's a clique on V union N of V. So that's the philosophy of this. Okay, so here's an example. There's a non-edge XY in N of V. It's shown as dotted red, so that's a non-edge. And there's a couple of edges XA, YB. I mean, there are more because there may be several edges between X and N2 of V. And we have a look at what's going on at the other end in N2 of V. So if AB is a non-edge, that edge in N2 of V, we can switch XA, YV at B to make XY an edge. So if AB is an unedge, we can do a triangle switch on the triangle V, on the paths VXA, VYB. If all possible triangle switches at V for the non-edge XY are blocked by edges AB in N of V, then We're going to use triangle switches to reconfigure the edges and non-edges induced by and between n of v and n2 of v, without ever reducing the number of edges induced by n of v. We may reformat the edges, move them around, but we don't reduce the number of them. So we have to make a series of moves, basically, using triangle switches to make AB a non-edge somehow, or some other edge which we'll do instead. Okay, so here's just one example of how to reconfigure edges and non-edges. So one nasty thing which can happen is that you have to imagine in this picture that x, y, and w are in n of v, and a and b are in n2 of v. So the vertex x has got neighbours a and b in n2 of v, but we're a bit stuck because there's a non-edge between a and b, but no other vertex in n of v has got a or b as a neighbour. So we can't really use that edge a, b, and n2 of v, because x is the only vertex with edges to a and b. Okay, so this just sketches out the way that we can sort of argue that we can turn that non-edge in AB, which has got a unique neighbour x in n of v, into a non-edge which has got two distinct neighbours x and w in n of v. It doesn't show how to actually make the final switch, but it shows a typical move which is used to break the kind of impasse. Okay, so x has got two neighbours in n2 of v because it's got a and b, so it must have a non-neighbour at y in n of v. In fact, it's got more than one non-neighbour because x has got a neighbour. X is a neighbour, has got an edge to v, and so it's got d minus one other edges, and x has got two neighbours in n2 of v, so it's got d minus three spare edges, and there are d minus one vertices in n of v, and it's got d minus, and it can have edges to at most d minus three of them. So somebody, and it's shown as the vertex y there, is a non-neighbour of x in n of v. Okay, so just for the simplicity of argument here, we're going to suppose further that all vertices of n of v have at least one neighbour in n of v. So like y, the vertex y, which edge has got x has got a non-edge to, has got a neighbour w. Okay, so y's got a neighbour w. Okay, so there's no edge wb because x is the unique neighbour of a and b. So now we've got a triangle switch at v to replace the xb, yw by the edges x, y, wb. So the actual triangle switch is at v, and there's a path of length to vxb, and there's a path of length to vyw, and so we can switch the edge xy with the edge wb, which moves the edges within the neighbour set of v from yw to xy, and now the edge AB, or the non-edge AB, has been freed up because it's no longer kind of stuck with only one neighbour in n of v. So this is a typical sort of move that you have to work out how to use, and there's about 4 or 5 of these moves that you have to make in order to sort of cover every case. But by making these simple arguments of 4 or 5 sort of simple arguments of this type, you can prove that you can always introduce another edge into n of v, and in this way you can eventually detach a clique at v. Okay, so just to sort of summarize the general case, what about if n's not congruent to 0 mod the d plus 1? Then that after you've done this sort of breaking off the kd plus 1s, you're going to be left with a bit of a little thing which is like what we call a fragment. So it's a size at least d plus 1, and it's size less than 2D plus 1, because the previous theorem covered 2D plus 1 or larger. So basically, you have to show that if you've got a tiny fragment like that, the sort of the chain on that small space is also connected, because that can be done as a separate construction. It's a separate proof that, you know, if the space is of that size between D plus 1 and 2D plus 1, then you can use triangle switches to get from any graph to any other graph in that space. And then the only other case is what if D is 1 or 2. So if D is 1, there are no triangle switches possible, because it's just matching edges, so there are no paths of length 2. And if D is 2, then it's very restricted, the space that you can carry out, sort of, which is irreducible. So n has to be 3, 6, or 7. So triangle switch chain is only irreducible if n is 3, 6, or 7. So basically, we restrict our attention to D greater than or equal to 3, and we've shown that. Well, we've shown in outline here that the space is irreducible, so that you can start wherever you like, and you can carry out triangle switches. And from now on, the hope is to prove that it's rapidly mixing, and then if we're really lucky to get some handle on the number of triangles or the stationary distribution of the graphs in the space. Okay, so that's the end of this brief talk. Thank you very much for listening. And don't forget, the papers are on the archive, or of course there's the IWOCA paper, which is actually, well, a longer version of that paper is available on the archive. If I can just stop recording.